We examine now ethylene as a monomer that has vital importance for the polymer industry. Now that word polymer in chemistry really refers to the plastics industry. You've been introduced to the term petrochemical industry in chemistry, and in Year 11 we really had a look at that petro side of the industry, petroleum, how we can use hydrocarbons as a source of fuel. We now in the HSC course major on the chemical side of that word, how we can use ethylene or ethene as the building block for the plastics industry. We will now examine ethene, how it forms polyethylene or polyethylene, and some other addition polymers. The first thing we need to examine is the process of polymerization. Now, polymerization is a chemical reaction in which many identical small molecules combine together to form one large molecule. If you'd like to picture it as follows, imagine a brick wall. Many individual identical bricks are needed to form an overall large brick wall molecule. If you, therefore, imagine the brick monomer, that would form the brick wall polymer. That's an idea of the polymerization process. So the small molecules in a polymer are called monomers, and the large resulting molecules are called polymers. If you're strong in English, you'll see that it's all in the word. Poly means many, mono means one. So a polymer is really many monomer units. Now here's an example of the polymer polyethylene. If you have a look at the top section of that picture, you'll see many monomer units of ethylene side by side. Down the bottom, under the arrow, they have all joined up or polymerized to form the overall big molecule polyethylene. We'll have a look at this process more closely. Polyethylene is formed from the monomer unit ethene. Remember, ethene is the systematic name of the monomer, ethylene is the IUPAC preferred name, two names for the same substance. If you have two of these monomers reacting, you can form the polymer polyethylene. The ethylene monomers have added together to form polyethylene via a process known as addition polymerization. It's a very simple polymerization technique. You are simply adding identical molecules together. So addition polymerization is a process that allows the formation of polymers without any loss of atoms. Notice that nothing else has been formed. No hydrogen gas or carbon dioxide, no water molecules. Everything at the top has simply been added to form the polymer at the bottom. Therefore, it's known as an addition polymerization process. Each polymer that results, therefore, is essentially a long alkane molecule, but here's the difference from what we studied in the prelim course. We're now dealing with polymers that may have a few thousand monomer units. Therefore, we're talking about very big, stable molecules. Now here's ethene, otherwise known as ethylene. You need to know this molecule inside out. You need to recognize it as ethene. Recognize it as belonging to the homologous series of the alkenes. You need to be able to draw it structurally. You need to be able to represent it as a molecule. You need to know it inside out. So whatever you need to do to learn this molecule, make sure that you can remember it. Polyethylene, therefore, is a long segment of ethene molecules joined together. You could represent this with a section of CH2 singly bonded to a CH2 parent or neighbour rather, in brackets to the n, where n is any number up to a few thousand. Now the addition process sees the double bond open out to form a bond with the neighbouring molecule. This double bond that used to exist in ethene has opened up and joined onto neighbouring molecules. The polymers are often written like this with the n, so that we're seeing a snapshot of a small section of the molecule that's repeated thousands of times. Polyethene, therefore, is the systematic name. Polyethylene is the IUPAC name. Now, the production of polyethylene is an important process for us in the HSC course. And there's two ways to produce polyethylene that will yield two very different polymers. The first process is sometimes referred to as the older process or the gas phase process. It's important to realise that this process has not been phased out, it simply yields a different product. The newer process is called the Ziegler-Natta process, which will yield a different form of polyethylene. So let's examine the processes together now. In the older gas phase process, ethene is vaporised at a temperature of about 300 degrees Celsius, which is fairly warm for this situation, and you need pressures up to 3,000 times atmospheric, so you need incredibly high pressure. In the newer process, the temperature is fairly low at 60 degrees Celsius, and the pressure is only 2 to 5 times atmospheric, so very different reaction conditions. In the older process, a molecule such as hydrogen peroxide or molecular oxygen is used to initiate the reaction, and the hydrogen peroxide and the oxygen are then incorporated into the final molecule. In the newer Ziegler-Natta process, a catalyst is used. One example of one might be triethyl aluminium. Now remember, a catalyst allows a reaction to proceed at a lower activation energy. Therefore, the catalyst allows the temperature and pressure to be lower because it enables a reaction to proceed more quickly with less energy required to achieve activation energy. Now here's the difference. The older process yields a substance that has what we call significant side chain branching. This means that the molecule will have a long linear chain in the middle, but some little branches coming off the side. We'll see a schematic representation of this in a moment. We call this low density polyethylene because the presence of the branches stops close packing together. The Ziegler-Natta process produces a polymer with no side chain branching. This means that neighbouring molecules can pack very closely together, which gives it a high density. This is abbreviated HDPE for high density polyethylene. We need to examine the difference between the two, and a good way to represent this is to imagine a logging truck. On the logging truck that you can see here, you've got many long centralised chains with no branches. They've been very tightly packed together. This would be an example of high density polyethylene. There's no side chain branching, so the centralised long carbon chains can be closely packed together. On the right hand side of the screen now, you can see an example of a tree that has its branches still attached. You could say that it has many side chain branches. On this truck you can only fit one tree, therefore it's a lot less dense than the truck on the left because there are side chain branches. So the leftmost picture could schematically represent high density polyethylene, no side chain branching. The picture on the right schematically represents low density polyethylene due to the presence of many branches. So we can see a relationship emerge. Side chain branching affects the density of the polymer. Why is this important? Well, here's another schematic representation. On the left, you've got linear molecules of high density polyethylene that have packed closely together. On the right, you have branched polymers with some side with some side chain branching that stops the polymer from packing closely together. Here are some schematic representations of low density and high density polyethylene. Another important thing that we need to acknowledge is the fact that you deal with average molecular weights for these particular polymers. What that means is that during the reaction process, you have ethene molecules reacting with neighbouring ethene molecules. But the point at which the chain terminates in the polymer, i.e. that moment at which that long hydrocarbon chain ceases to add any more ethene molecules, that moment is random. That means that you'll have some molecules that are fairly long and some that are shorter. Therefore, when we refer to the molecular weight of polyethylene, we have to refer to it as an average length because there's no defined specific length of the polymer. I like to think of it like this. Imagine you have a tin of spaghetti. If you emptied the tin of spaghetti onto a plate and lined all the lengths of spaghetti up next to each other and measured them with a ruler, you would find some would be 8 centimetres, some would be 12, 16, 4, etc. You would be able to refer to the average length of a spaghetti piece in a tin by adding them all up and dividing by the number that you have and calculating the average. That's what we do with polyethylene. We would take a sample. There would be many different polymer lengths, so those lengths would be averaged out and you would refer to that sample as an average molecular weight. Here's a graph indicating as such. On the x-axis you have the molecular weight, on the y you have the number of polymers that have that molecular weight. You can see a nice bell curve distribution that says the smallest, the shortest polymers in this sample would be about 20,000, whereas the longest would be about 80,000. But by far, the middle of that bell curve, we're told the average of all those lengths in the sample comes out at about 46,000. Therefore, for this sample of polyethylene, the average molecular weight is 46,000 grams per mole. Now, why is that important? Well, you need to know that the average molecular weight of polyethylene is a good representation of the molecule because the nature of the collisions of the monomers in the reaction process are random. Because they are random, we end up with lengths of the polymer that are different, so an average must be used to represent them. So here's a summary of what we've learnt so far. Ethylene is the monomer that polymerizes to polyethylene, and it does so via addition. The Ziegler-Natta process gives us high-density polyethylene with no branches. The gas phase or older process gives us low-density polyethylene that is highly branched. The double bond opens out to form long alkane chains. The polymer chains vary in length due to the random collisions during polymerization. Here is an overall schematic representation of a section of polyethylene. Now, another polymer that we need to examine, the second addition polymer, is polyvinyl chloride. You might be used to hearing about it as PVC. Have a look on the screen. There is the monomer unit of polyvinyl chloride. Notice that it's very similar to ethene. What's the difference? Well, one of the hydrogens attached to the second carbon has been replaced with a chlorine atom. That's the only difference. Now we have a monomer here that we could refer to as chloroethene, indicating one chlorine atom bonded to the ethene molecule. That's the systematic name. The IUPAC preferred name is vinyl chloride. You need to be able to recognise it and name it in both of these forms. The hydrogen atom has been replaced by a chlorine atom. Now this is a very cheap polymer to produce, and it is therefore the second most common polymer in the plastics industry due to the cheapness of its production. We're used to seeing it as pipes for internal guttering and plumbing, and we'll examine some of those properties shortly. Now, this is an addition polymer, so it follows the same rules as the production of polyethylene in that it simply adds neighbouring monomers together to form a polymer with no loss of atoms. Have a look. It will polymerize around the double bond such that the double bond opens out to form a long, straight hydrocarbon chain, but this time we're going to have chlorine atoms off to the side. So the structure at the bottom of screen now shows a long hydrocarbon backbone. Notice that every second carbon in the monomers have a chlorine atom attached, so every second carbon in the polymer has a chlorine atom attached in the place of a hydrogen. The polymer is still saturated in that it has single bonds, but it has chlorine atoms on every second carbon. That is a section of the addition polymer, polyvinyl chloride. Many vinyl chloride monomers or many chloroethenes. You could represent it then as a section of chloroethene in brackets to the n, where n represents a number from a few hundred to a few thousand. Now the third addition polymer that you need to be familiar with is called polystyrene. You're used to seeing polystyrene in packaging and insulation. This is a slightly more complex monomer. If you have a look again, identify at the top of the monomer you've got your familiar structure of ethene. Again, one of the hydrogens has been replaced, but this time by a fairly complex cyclical structure, a benzene ring. You could represent it in an abbreviated form where you see that you've got 6 carbons and 5 hydrogens hanging off that second carbon in the same place that the chlorine atom did in vinyl chloride, but this time you've got styrene. So styrene is the name of this monomer. It's the ethene molecule with a hydrogen replaced by a benzene ring. Now the benzene ring is actually more accurately referred to as a phenyl group. Phenyl is what you get when you remove a hydrogen from the benzene group. Now that's sounding a little bit more complex, so I will explain it in this way. Have a look on the screen now. You have a benzene ring. Notice you've got C6H6. If I was to remove one of the hydrogens, it would become an alkyl in the same way that if we removed a hydrogen from a familiar hydrocarbon, it becomes an alkyl. So here's ethane on the screen. If I remove a hydrogen from ethane, I get ethyl. If I remove a hydrogen from benzene, I get benzyl or phenyl. So there it is, I've removed the hydrogen at the top. This is now called phenyl. Let me do that again for you. If I remove that hydrogen, I get phenyl. There's benzene, here's phenyl. Because I've removed that hydrogen, that carbon now wishes to bond with a neighbouring molecule, and it does so by bonding to ethene. Now we can abbreviate the styrene monomer to the structure you see on the right of screen. You have the parent ethene molecule. It's had a hydrogen replaced by the side group phenyl, so that you now have styrene. Note that the styrene is still ethylene. It's simply got this hexagonal structure attached in the place of a hydrogen. Now there's an example of a section of the polymer polystyrene, because you've got many styrenes. Notice you've got a hydrocarbon backbone. Every second carbon has 2 hydrogens attached, but every other carbon has had one of the hydrogens replaced with a side group called styrene. Therefore, polystyrene is hundreds or thousands of these monomers all joined together. This again is an addition polymer where the double bond opens out and everything is added to one another with no loss of atom. The IUPAC name is polystyrene. The systematic name is phenylethene because you have a phenyl group attached to an ethene monomer. So for the whole polymer, it would be polyphenylethene. Easy? We'll have to do some study. You need to be able to discuss all of these as addition polymers. So here's a quick discussion on a single slide. Polyethylene and polyethene have the monomer ethene. The polymer, therefore, looks like a long alkane hydrocarbon chain. Very simple. There are 2 forms, remember, high density and low density polyethylene, depending on the presence of side chain branching, which is decided by which process is used to form it. The older gas phase produces side chain branching, the newer Ziegler-Natta produces linear molecules. Polyvinyl chloride, PVC, or chloroethene, all the same thing, have this monomer, chloroethene. It forms, therefore, a section of the polymer that you can see on the right of screen, polyvinyl chloride. Polystyrene is slightly more complex. It's the one with the hexagonal ring hanging off the ethene molecule. Therefore, it forms a nice complex structure, such as the right of screen, polystyrene. So those are your 3 addition polymers that you must know for the HSC course. We will discuss them at length in the next video. You need to be able to recognise them and draw them as such.